All right, so day 4 notes here. It's all about weak bases. Weak bases have a very similar concept related to weak acids, except we're dealing with a base and not an acid. How we identify we have a weak base is that it accepts the H plus, and how we distinguish it from a strong base, it is not a hydroxide compound. So in this case, NH3 is our weak base. It's, again, a base, and it doesn't have that OH or that hydroxide attached to it, okay? So I always like to emphasize this with our equilibrium expressions. I always like to write out our particular K or equilibrium expression here. So just as a reminder, we'd have big giant K, products over reactants, and so you'd have NH4 with a 1 plus there, times our concentration of hydroxide ions all over ammonia or NH3. Again, we don't include water because it's a liquid, and I want you to note this. This is exactly the opposite of what we saw in a weak acid problem. In this case, water, H2O, acts as the acid. One of the H's is donated to the base, the NH3, and we get this. Unlike in acids where we got an H3O plus, now when we have a weak base problem, we get OH minus, okay? The other thing I want to point out is this. We call this KB, B standing for base, to distinguish our base versus our acid, okay? Now, before I go to the next section here, if we can only get the concentration of OH minus, at the end of the day, do we find pH or POH based on that number? POH, all right? So just some things, little minor things to keep in mind as we go through this. Questions? Does anybody need it? All right, so here we go on this. Again, this is essentially a copy and paste from the weak acids, except we put a B for base instead of an A for acid. The bigger the K, the stronger the base is, right? For weak bases, it's going to be close to 1 as possible. For our weak or strong bases, for our weak bases, you are going to have a really, really tiny K. When I say tiny, it's like 10 to the negative 10th power. Okay? Questions over any of this? All right. Does anybody still need it? All right. So let's go ahead and let's jump into an actual problem. We want, in this problem, just the concentration of hydroxide ions, OH minus, in a 0.15 molar solution of NH3. Now, we have NH3, which on a previous example, we said, hey, this is a weak base. And I always like to start out by writing our equilibrium equation. And so with our equilibrium equation, we again have this. We have NH3, which we saw was AQ, is aqueous, okay? Then we have this combined with water, H2O, that's a liquid there. Water acts as our acid, so it gives away one of its H's, and we end up with NH4 with a 1 plus. That's aqueous. And we end up with our OH 1 minus, which is also aqueous. Okay? So we have our setup. Now, I've told you before, but I'll remind you, equilibrium problems or when we see our equilibrium arrows, are going to require our ice chart. So immediately I just go ahead, if I see equilibrium, I know I'm going to have to use that ice chart in some way, shape, or form. Okay. Now, before we get too much further into this, I want to emphasize this. NH3, we don't get a whole lot of information, but on your equilibrium constants, most of this page, actually all of the front page, is Ka. On the back side, just a little section is Kb. And so on this chart, since I didn't give it to you, you would have to look this up. But the Kb for NH3, our Kb is 1.8 times 10 to the negative fifth. So 1.8 times 10 to the negative fifth. Okay, so that's important as we go through and we solve this. So if I don't give the Kb or Ka value, it's on our given sheet. Okay, now what's the only thing that we're given in this problem, number wise?
0.15.
Yep, and it's 0.15 NH3. Well, if we're not given anything, what can we assume our other quantities are? 0. Okay. Now, we go through this, and I'll ask you this. Do we know our particular change during this problem? Do we have anything that could give us a numerical change? We don't. So we have to assume that this is going to be an X. Okay. We got to lose some of this original 0.15, and so we're going to minus an X. Over here on the right-hand side, since we started with 0, we have to gain some. We don't know how much, and so we have X and X. Now, at equilibrium, we have the following. We have 0.15 molar minus X. We have X, and we have X. Okay? If we can start to forecast this out, if we plug this back in to our equilibrium expression, we would have to use the quadratic. However, if we take our assumption, which I'm going to verbally go over it. Does anybody need me to write down the assumption? Good. All right. So if we take Kb times 100, so if we take 1.8 times 10 to the negative fifth, and we multiply that by 100, it needs to be much smaller than our original concentration of 0.15. When I take Kb times 100, I get 0.0018. Is that number smaller than 0.15?
Yeah.
Yep. Okay. So what I like to do is this. Assumption, I'm going to try to generally make work, but we could cross out this minus X part because our assumption works. Okay. All right, so now let's get down to business with this. Again, I know we just wrote down the equilibrium expression here, but I'm going to rewrite it so we can insert our numbers into our formula. So this time here, we have Kb equals our NH4 with a 1 plus times our OH with a 1 minus, all divided by that original base concentration, which is NH3. Okay. From here, all I'm going to do is I'm going to just solve or insert our values here, and we would end up with this. Out in front, our Kb value is exactly what is from our particular chart there. And so we would have 1.8 times 10 to the negative fifth equal to X times X all divided by just 0.15 molar. Okay, we got rid of the minus X because of the assumption. Now, is everyone okay if I just give what X equals? Or does anybody need me to see me do the math? Good with just what X equals. We solve this mathematically, and our X ends up being 1.6 times 10 to the negative third. Okay, so our X equals 1.6 times 10 to the negative third. And so what's the so what out of that X? What is X really equal to that we're after? The OH, all right? So this is the concentration of our OH minus, okay? And we could put that as big M for molarity. Now, with our OH minus, with what I just boxed in here, remind me again what value I could solve for. Could I solve for the pH or the POH using this value here? POH, right? So it's just some minor differences in our bases versus our acids in terms of weak acids, weak bases. Questions? Does anybody need this? All right, let's throw a little bit more complexity into this, and let's talk about really a more realistic item that's going to happen here in chemistry, and that's when our particular chemicals are dissolved in substances that already have a particular ion. All right, so let's think about dissolving items in a lake, right? We have a compound that we're interested in, but already there's other items, other ions, and as a result, our initial quantities are going to be different. So you can see our example here. If you take KCl, KCl is not an acid or a base because if you notice, nobody donates a proton, nobody accepts a proton. However, Cl minus is a conjugate base to a very, very strong acid, and as a result, would affect the pH in this. So pH can be affected by other ions that are already in our particular solution. As a result, changes either up or down on the pH is going to occur. Okay, and then that middle statement there, typically the anion, the negative ion, is going to affect both the pH and how much base we have present. All right. Questions on this? Does anybody need them? All right, so last problem of the day here. I'm going to highlight some things before we really get going. So just kind of hold tight here. We have solid sodium hypochlorite, okay, NaCl, and we dissolve it in enough water to make 2 liters of a solution. At the end of the day, we want that solution to have a pH of 10.50. We want to use this information with the equilibrium expression to calculate how many moles of sodium hypochlorite we need to add to our water, and the Kb for this weak base is 3.3 times 10 to the negative 7. Just want to highlight a few things, one of which is this. Our value at the end, we're going to have to do something with 2 liters, okay? So remember that at the end, it's going to affect kind of our final item that we have to worry about. And now chemistry, I want to talk about what's happening here. We are taking this compound and we're putting it in water. Now, Does anybody remember what happens to an ionic compound as it is dissolved in water? It splits into what? Salt water, sodium chloride. I put it in water.
Separates.
There we go. It separates. Very good. So this is going to separate into Na with a 1+ charge, and it's going to separate into that ClO with a 1- charge. So my point is this, that ClO-, where we're getting it from in this equation right here, is from when we dissolve this whole NaClO in water. It is separating, and that's where we're essentially getting our starting base to go through our acid-base part here. Now, we get to an equilibrium expression, which is what our weak bases give us. And what chart are we going to have to use for this?
Ice.
Very good. Our ice chart. So I'm going to automatically go through. I'm going to give some decent amount of room. Our I, C, and our E. And this is where we have to think about this. All right. Right now, we don't know how much of this NaClO we have. So we're going to have to get to that here in a second. Just keep that in the back of your mind. The only thing that we are given is that we know that the solution has a pH of 10.50. Now, if we think about the pH formula, pH equals negative log of H3O plus. In our equation, does anybody see H3O plus? No. So we right now, we can't take that information and make it useful, but what we can do is this. We can say, hey, we know that 14 equals our pH, which I'm going to go ahead and replace with 10.50, plus our pOH. So now how do we solve for, or how do we find our pOH? Subtract that 10.50 on both sides. And so when we do that, we end up with 3.50 equals our pOH. All right. Now, what we can do from here becomes really, really useful to find out some value in our equilibrium expression. So remember, our pH, or excuse me, our pOH is 3.50 equals the negative log of our hydroxide ions at equilibrium. Okay, so if I go through this and I say this, and remember, key thing here, I just go ahead and I make this number the opposite, negative. And so I'm going to take the inverse log, which is 10 to the x. So 10 to the x, negative 3.5. And going to use scientific notation. I get a value, I'm going to round it to sig figs, of 3.2 times 10 to the negative fourth. Okay, so the concentration of OH minus is, or excuse me, 3.2 times 10 to the negative fourth, big M. All right, that is our equilibrium amount of OH minus. So I'm going to take the time here and I'm going to say this. All right, we have 3.2 times 10 to the negative fourth, big capital M. All right, now think about the chemistry that's happening. We dissolve the sodium hypochlorite and we start out with some amount of ClO. Well, if we start out, which I don't know yet, our amount of ClO, do we have anything on our right-hand side? If we start out with really ClO. We don't, so we can assume this. We can assume that both of these initial quantities are 0. And so to go from 0 to 3.2 times 10 to the negative fourth, how much did that OH minus have to gain?
3.2.
Exactly the same amount. So we can say plus 3.2 times 10 to the negative fourth m. Well, HClO, they're 1-to-1 coefficients. So how much did HClO gain from initial to that equilibrium? Yep, exact same quantity, which means our items of interest on the right-hand side are already solved for, and we know the equilibrium concentration, okay? Now, while we're talking about change, I'm going to go ahead and I'm going to actually talk about our C for change before we even talk about our initial and equilibrium value here. So if our right-hand side is gaining, our left-hand side has to be doing what? Very good. Losing, and it's still a 1-to-1 coefficient, so how much will this side lose? 3.2 times 10 to the negative fourth, big capital M. Now here is a very odd part. Normally, we either have an initial value or we assume it's 0. But remember, we're trying to figure out, hey, how much of this stuff should we dissolve? So what we're really after in this problem is we're really after, hey, initially, how much should we have? So this becomes our X. At equilibrium, then, we get our X minus 3.2 times 10 to the negative fourth, big capital M. So again, I always like to draw my picture here, put my formula, and so I go ahead and write out my KB in this process here. So for this process, our KB is equal to HClO times our hydroxide, our OH minus, all divided by ClO to the minus there. Okay. Now all I'm going to do is insert these values back into my expression here. So we start out with our KB that's given at the top of the problem, and we have this. We have 3.3 times 10 to the negative seventh equals our value for both HClO and OH minus, which I'm going to write this down twice. If you just want to put it in as square, that's as fine too. But we have 3.2 times 10 to the negative fourth, big capital M, times that same value for our OH minus, which is 3.2 times 10 to the negative fourth, big capital M. All divided by X minus 3.2 times 10 to the negative fourth, again, big capital M. From here, all this becomes is just algebra, all right? I can walk through and solve this, but is anybody opposed to me just giving you what X becomes? You good? All right, I can walk through the algebra with you. Just let me know. But at the end of the day here, our X just becomes 0.303. All right? X equals 0.303. And what that really is the concentration of ClO to the minus. All right? That's a big capital M of our concentration of ClO to the minus. All right. Now, if you do take this calculation, how I got 0.303 is every time I do my multiplication, I round to 2 sig figs. Okay. So that's how I get 0.303. If you keep it in your calculator, you get a little bit bigger number. I round each time here. To answer the question here, though, we want to know, okay, yeah, this is our molarity, but we want to know how many specific moles that we need to worry about in 2 liters. So out to the side here, last part here is this. Molarity, big M, is equal to what divided by what? For molarity, we have mole over volume, which is in L for liters. Yes. Okay. So all we have to do on the final part here is we're going to take our 0.303. We're going to take 0.303 big M equals our X number of moles all over 2.00 liters. Now, we would cross multiply, and our number of moles would be double this at 0.606 moles, and this specifically would be moles of this substance that we have to dissolve. Now, again, Na, sodium, has no effect on the pH, and a lot of positive ions don't, but we still get that 0.606 moles of ClO minus to go through that. All right? Questions?